All right, today we're going to talk about the last topic of the summer, which is, if I can write properly, let's try that again, which is convergence of infinite geometric series. Right? So an infinite geometric series. What is an infinite geometric series? Well, first of all, we know that a geometric series, right, is going to be a sub 1, right? We have a seed value, plus a sub 2 times our ratio, our common ratio, right? Plus a sub 3, sorry, each one of these should be a sub 1. I keep doing that. So a sub 1 times r plus a sub 1 times r squared, and so forth, right? Plus ultimately a sub 1 times r to the n minus 1, right? All right, so that would be a geometric series, but this is going to be a finite one because n, we're assuming, is some finite number. Now, on the other hand, if we just keep on going, right? So if I go ahead here, and instead of being s sub n, because we're not going to stop at n anymore, if I just keep on going, right, and I just do plot, sorry, I got to go back and fix this really quick, and I just go ahead and do plus dot dot dot, that indicates that we're just going to keep on going forever, right? And so the way that we can notate, so with infinite geometric series, it's sort of clunky to write them out just by, writing out all the terms here, or showing the pattern, putting the dot dot dots in. If we don't want to have the dot dot dots and we just want a closed form version of this, we can use sigma notation, right? We can say sigma means we're adding up a whole bunch of stuff. We're going to go from the first term, so k equals 1, all the way to infinity now. Instead of stopping at a finite value, we're just going to keep on going forever and ever and ever, right? And we're going to add up the term a sub r times r to the k minus 1. And right, so for the first term, let's just make sure this works, right? For the first term here, we have a sub 1 times k to the 1 minus 1, which is, sorry, r to the 1 minus 1, which is going to be 0. Which would just going to give us a to the 1 there. So that works for the first term, and it makes sense for the rest of the terms as well. All right, so this is the sigma notation version of that, right? And so earlier, or yesterday, and so the question becomes, I guess, is if we keep adding these terms over and over and over again, is this series, is this sum going to converge to a specific value, right? Or is it just going to go off to, if we just keep adding these values, is the sum just going to keep increasing forever until, it goes off to infinity? So does it converge or does it diverge? Right? So converge, let's just, an infinite series converges if it goes to some finite value as n goes off to infinity, right? So instead of just continuing to grow forever, it eventually stops growing and approaches some finite value. And otherwise it diverges. Whoops. Right? So in the case of a finite series, right? Let's say I have a finite geometric series, which would be notated like this, k equals 1 to n, right? As opposed to infinity, some finite value n of a sub 1 times r to the k minus 1, right? We know that, and so we'll call this is s sub n. We know the other day we derived a formula for what that sum actually was, right? It was a sub 1 times 1 minus r to the n over 1 minus r. So the question becomes, right, as n, I keep doing that. Sorry, I'm going to go ahead and erase this. So the question becomes, as n goes off to infinity, what happens to s sub n, right? That's the big question of the day. So that is a really informal way of writing a limit, right? So the question is, what is the, and so to form this in a really like sort of mathematical way, to ask this same question, we'd say, what is the limit as n goes to infinity of s sub n, right? Which is the same, instead of saying s sub n, we'll say the limit as n goes to infinity. I'm going to go ahead and do this on the next page, actually. So, as n goes to infinity of s sub n, which, based on the formula, if s sub n is a geometric series, right, then s sub n is the same as a sub 1 times 1 minus r to the n over 1 minus r. So the question is, what is happening to this expression right here as n gets really, really big, right? And so that really depends on where n shows up in our expression here. And we see that the only place n shows up in the expression is right here, right, is right here. And so the question becomes, what's happening as this exponent gets really large? And does it depend on what r is, right? So, let's think about this. As, depending on what r is, as n gets really, really large, r might get really, really big, negatively, of course, or r might get really, really small, right? Examples would be, well, what if I have like 1/2 to the n? As n gets really, really big, so let's say the limit as n goes to infinity of 1/2 to the n, what's happening there? Well, as n gets really, really big, 1/2 to the n is becoming what? It's really, really small. So it's eventually, as n goes to infinity, it's going to go to 0, right? On the other hand, as n goes to infinity for an expression like 2 to the n, right? As n gets really, really big, what's happening? Yeah, we're just going to keep growing. It's going to go off to infinity. So, right, we would say that, you know, if we have this type of behavior, this is probably a situation where the series is going to converge if it's not going to grow forever. But if something's going to grow forever, it's probably going to diverge. Now, so if we're looking at this situation right here, it really all depends on what r is. So we're seeing that if r is a number between 0 and 1, right, then it's going to go to 0 and go away. On the other hand, if r is bigger than 1, then it's probably not going to be the case. So let's say if r is between 0 and 1, the limit as n goes to infinity, right, is going to be a sub 1 times 1 minus r to the n over 1 minus r is going to be the same. It's just going to be, well, what's going to happen? A is a constant. That's not changing. R is a constant value. That's not changing. The only thing that's changing here is n, right? So as n goes to infinity, r to the n is just going to become, as we talked about here, if r is between 0 and 1, it's just going to become 0, right? And if that's the case, I'll just end up with a to the 1 over 1 minus r. And because this is a finite number, right, because this series goes to a finite number as n goes off to infinity, that meets our definition of a convergent series, right? So we'd say the series converges. Now, on the other hand, if r is greater than 1, then the limit as n goes to infinity of a sub 1 times 1 minus r to the n over 1 minus r, right? Well, r to the n is just going to blow up, right? R to the n is just going to get really, really, well, negative in this case. And this is never going to converge to a number. It's actually going to go off to, right? Well, depending on what r is, really. It's not going to converge, though. So it's either going to go to negative or positive infinity. Whether it goes to negative or positive infinity depends on, well, this will be negative, and this will also be negative. So it's going to go off to infinity, right, under this circumstance, right, because the limit's going to equal infinity. So this would be a divergent series. If r is greater than 1, then your geometric series is going to diverge, right? What if r is, on the other hand, let's think of one more situation here. If r is between 0, sorry. What if r is between negative 1 and 0? What's going to happen here? Right, let's think about that. What if I had like negative 1/2 to the n? What's the limit of that going to be as n goes to infinity? Well, because this is a negative, because we have a negative base here, we know, and n is going to be an integer value because this is a series, right? It's going to alternate signs over and over again. But as it alternates signs, what's going to happen to the absolute value of this expression? Yeah, it's going to get smaller and smaller. So even though it's alternating back and forth, you know, if here's, right, here's 0, right, negative 1/2 squared is going to be somewhere over here, and then negative 1/2 to the third is going to be over here. But the numbers are going to be getting progressively closer to 0. And so eventually, even though it's alternating on both sides of the 0, it's going to get closer and closer to 0. And it is eventually going to get to 0 as well. So we would say that if that's the case, then the limit as n goes to infinity of a sub 1 times 1 minus r to the n over 1 minus r is also going to be, this is also going to go down to 0, and it's also going to be a to the 1 over 1 minus r, right? And it's going to be a convergent geometric series. And lastly, the last scenario, well, what if r is less than negative 1, right? So what if it's like negative 2 to the n, right? Well, if it's negative 2 to the n, what's going to happen? It's going to do this same thing where it's going to be going from opposites. It's going to go and, you know, go back and forth between the two sides of 0, but it's going to get farther and farther away because this absolute value of this quantity is going to be growing. And so, but the thing about it is it's not really going to positive or negative infinity because it keeps flipping back and forth. So it truly converges in every, or diverges, I should say, in every sense. And so for this one, we're just going to say that the limit just does not exist at all. It doesn't even go to infinity or negative infinity because it just keeps switching sides of the coordinate plane. So it does not exist. All right, so we would say that in this case, the limit as n goes to infinity of the sum of our infinite geometric series, or our geometric series, is also not going to exist. And because that limit doesn't exist, it's also going to be convergent. So, to sort of break this down and summarize it, right? So we know that if it's between negative 1 and 0, it converges. If r is between 0 and 1, it converges. So a way to capture all that, we could either say if r is between negative 1 or 1, or we could say if the absolute value of r is less than 1, which captures everything between negative 1 and 1, then the geometric series will converge. right? On the other hand, if the absolute value of r is greater than 1, right, then the geometric, or sorry, greater than or equal to 1, then the series, the geometric series, because this just applies to geometric series, will diverge. Right? So that's how we determine whether a series is divergent or convergent. Let me ask you, now that we've talked about what it means to diverge or converge, let me ask you a conceptual question. Because this idea of divergence and convergence, we usually talk about it with respect to geometric series, but the idea applies to any series, any infinite series. So will an infinite arithmetic series converge or diverge? Will an infinite arithmetic series converge or diverge? So an example of an arithmetic series would be like 2 plus 5 plus 8 plus 11, right, dot, 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 all the way out to infinity. Is that going to converge or diverge? It's going to be divergent. Yeah, it's never going to converge to a specific value. It's just going to continue to grow, and it's going to grow faster and faster as n gets larger and larger. So arithmetic series, they always diverge. So because they always diverge, no matter what type of arithmetic series you're talking about, it's kind of boring to talk about their convergence or divergence because they just always diverge. Whereas geometric series can actually potentially converge, which that's more interesting than just having the series always diverge. And then whether any other type of series will converge or diverge, it really depends on the series, right? And a large portion of BC calculus will be devoted to do all these other types of series that you're going to study, do they diverge, do they converge? And you're going to have to just know a whole lot about a whole lot of different types of series because they all behave differently. So, but whether a series diverges or converges becomes a really important question in calculus. And this is your first example of a divergent example. So for example, let's say we have the infinite geometric series k equals 1 to infinity of 2 times 2/3 to the k minus 1, right, which if you write that out is 2 plus 4/3 plus 8/9 plus dot dot dot, right? Answer the question, does it diverge or converge? So does it converge? If so, find its sum. So give that a shot. All right, so does it converge? First of all, let's identify a sub 1 in this case is going to be equal to 2, and r is going to be equal to 2/3. So because the absolute value of r in this case is less than 1, we conclude that the series converges. Right? So that's good. And so if it does converge, if we do have a convergent series, then the sum from k equals 1 to infinity of 2 times 2/3 the k minus 1 we know is going to be equal to, right, a sub 1 over, right, 1 minus r. That was the formula that we derived in that last part there. So a sub 1 over 1 minus r, right, and so we'll end up with 2 over 1 minus 2/3 is going to be 1/3, and so we get 6. So it's going to end up, if we add up an infinite number of terms, it'll eventually add up to 6. Sort of a funny thing to say, because we know it's never going to get there, because can you ever actually get to infinity? No, but eventually if you could get to infinity, it would get to 6. So it's sort of a weird statement to make, but it is true. Let me ask an interesting question. What is 0.9 bar the same as? Anyone know the answer to that question? What is 0.9 bar? So some people know that 0.9 bar, and by the way, So some people know that 0.9 bar is the same as 1, right? They're making the statement that 0.999, if it goes off to infinity, equals 1. Can we prove that? Right? There actually is a pretty quick algebraic proof, right? I shouldn't say example, I should say proof, which I'll review really quickly. Some of you have probably seen this already, which is we start off with n equals 0.999 ... Right? Then we're going to go ahead and we're going to multiply both sides by 10. Right? And we realize that 9.999 is the same as 9 plus 0.999, right? And so at the same time, we had earlier defined n to be equal to that. So we're going to do a substitution here and say that's equal to 9 plus n. And we see that we end up getting 9. If we subtract the n from both sides, we get 9n equals 9, and therefore n equals 1. So that's a pretty convincing algebraic proof that n does that 0.999 does in fact equal 1. That's an algebraic proof. But the cool part is that there's a bunch of different ways to prove that, and one of the ways to prove that, right, is using an infinite geometric series. So let's take a look at that. So the geometric series proof of the fact that 0.999 ... is equal to 1, right? So we start off with the fact that we want to try and break this down and think of it as a series. So 0.999 ... is the same as 0.9, right, plus 0.09 plus 0.009. I think you see what I'm getting at this point. All the way out to infinity, right? So if we just keep adding the next smallest place value of 9 here as we go on, and we keep doing that forever. So what I want you to try and do is go ahead and write this out, find the sort of the sigma notation for this geometric series, right? Because we can see it is you'll see in a second, it is a geometric series. Find the sigma notation for that. Determine, prove whether or not it diverges or converges. Hint, it should probably converge, right? And once you've done that, use what you know about geometric series to find what it sums up to. All right, so give that a shot. So the first thing we want to do here, as I said before, is we want to write this in terms of a geometric series. So what we can do here is, first of all, think about this in terms of powers of 10. Right, so 9 is 9/10. 0.09 is 9 100ths. 0.009 is 9 1,000ths, and so on, right? So that's 9 over 10, 9 over 10 squared, 9 over 10 cubed. And so we're seeing that we can probably see our ratio right here starting up. Right, so if we want to write... All right, so I wasn't recording this, so I'm just going to talk you guys through it. So we started off, we have 9/10 plus 9 100ths plus 9 1,000ths plus ... right? That's the same as 0.9, 0.09, 0.009. We realize the bottom, we just have powers of 10, so let's write them as powers of 10. 10 to the 1, 10 to the 2, 10 to the 3, and so forth. And so I can write that as the infinite series as k equals 1 to infinity of just 9 over 10 to the k, right? Because we have just 9 over 10 to the 1 plus 9 over 10 to the 2, and so k is equal to 1, k is equal to 2, k is equal to 3, and so forth. And this adds it all up all the way out to infinity. That's where the ... comes in. right? And we want to write this in the form of a geometric series, so we want to factor out what our a sub 1 is, which is 9/10 here. So if I factor out my 9/10, what I have left on the inside is 1 over 10 to the k minus 1, right? Because 10 to the k, if I take out 10, 10 times 10 to the k minus 1 is the same as 10 to the k, right? And lastly, I'm just going to write this, instead of saying 1 over 10 to the k minus 1, I want to say the whole thing, 1/10 to the k minus 1, because it doesn't matter, 1 can be raised to anything, right? It doesn't change anything. So the k minus 1 might as well be on the outside. And that means that our a sub 1 value is 9/10, and our common ratio that we always need to determine the behavior of a geometric series is 1/10, right? Because the common ratio is between -1 and 1, we know that the series converges. And because the series converges, right, we know that the formula for the sum of the series is going to be a sub 1 over 1 minus r. And so on the next page, and so we take our series, I'm just going to rewrite it. So here's our series again, rewriting the series. And it's equal to a sub 1 over 1 minus r. So our a sub 1 was 9/10, our r was 1/10, so a sub 1 over 1 minus r. Let's go ahead and simplify this. 1 minus 1/10 is just 9/10. And of course, 9/10 divided by 9/10 is equal to 1. So we've now just proven, right, that 0.999, which is the series representation of 0.999 dot dot dot, is equal to 1. And so in many cases, we can use infinite series if they converge to prove certain things like this and similar to this. And you'll do that again in calculus as well once you get to BC calculus. So that's that. All right, so let's look at a word problem now that is going to require us to use what we know about infinite geometric series here. So we have a pendulum, and there's a picture of the pendulum right there, just to your left, and it swings an arc of 18 inches, as we see there. On each successive swing, the length of the arc is 0.98 of the previous length, right? So what is the length of the arc in the 10th swing? On which swing is the length of the arc less than 12 inches? Or sorry, which swing is the length of the arc first less than 12 inches? After 15 swings, what total distance will the pendulum have swung? And when it stops, what total distance will the pendulum have swung? So as we can see, it's getting smaller, so eventually it is going to stop. And so you're going to have to use what you know about infinite geometric series to solve this problem. So see what you can do. All right, so part A, first of all, what is the length of the arc of the 10th swing? So in the first swing, it's 18 inches. On the second swing, it's going to be 18 times 0.98. On the third swing, it's going to be 18 times 0.98 times 0.98, which is the same as just multiplying by 0.98 two times, right? And so I think we can probably extrapolate out there that on the 10th swing, it's going to be 18 times 0.98 to the what? So on the first swing, second swing, third swing, we see we have n minus 1 right there, right? So on the nth swing, that's what it's going to be. So on the 10th swing, it's going to be 18 times 0.98 to the 9th, right? Which will give us 15.007 inches on the 10th swing, okay? So part B, we already said that on the nth swing, it's going to be 0.98 times to the n minus 1 inches. And the question is when, on which swing is the length of the arc first less than 12? So if we can figure out when it's equal to 12, right, then it's going to be less than 12 on the swing after that, right? So if we set that equal to 12, we now have an exponential equation that we can then go ahead and solve. So we end up getting 0.98 to the n minus 1 is equal to 12/18 if we divide off the 18, which is going to be 6/9 or 2/3, right? And then if we go ahead and take ln of both sides, we can get n minus 1 times ln of 0.98 is equal to ln of 2/3. I could just have easily have used log base 10, but I chose natural log just for the heck of it. And so I'm going to rewrite that in the next page here. I have n minus 1 times ln of 0.98 is equal to 2/3. We want to solve for n, so we'll go ahead and divide off the ln, whoops, that's ln of 2/3. We divide off the ln of 0.98, and then we can go ahead and add 1. This over here. And so we get that n is equal to ln 2/3 over ln 0.98 plus 1, which is approximately equal to 21.07 swings. Right, so if it's exactly equal to it on the 21.07th swing, that means it's still going to be greater than it on the 21st swing, and the 22nd swing of the pendulum is the one where it will first be less than that. So the 22nd swing. Okay, part C asked us, I'll do this farther up here so we can get more room. Part C asked, after 15 swings, what total distance will the pendulum have swung? All right, so on each, so we're essentially, instead of just looking at each swing individually, we're going to start adding them up. And so the first swing, we have 18 inches. Right, the second swing, we have 18 times 0.98 inches. So that after the second swing, that's the total distance it would have traveled. After the third swing, right, that's the total distance it would have traveled. And so we keep adding that up, right, that's equal to the sum as k equals 1, 2. And if we want to go all the way out to the, we want to figure out what happened on the 15th, or how long, how far is it done after 15 swings, we're going to go out to 18 times 0.98 to the 14, right, n minus 1 there. And so we want k equals 1 to the 15th of 18 times 0.98 to the k minus 1. Right, that's going to be our series right there. And so using our series sum, we know that's going to be equal to a sub 1 times 1 minus r, r being 0.98, 0.98 to the n, all over 1 minus 0.98. And that's going to be about equal to, that's about equal to 235.3 inches. Okay, so after 15 swings, it will have swung 253.3 inches. And lastly, the question is, when it stops, what total distance will the pendulum have swung? So we accept the fact that if the length of its swing is getting shorter and shorter, eventually the pendulum is going to stop because it's slowing down, right? So the question is, how long will it have swung when it does stop? So essentially we're asking the question, what is the sum as k goes from 1 to infinity? We're essentially asking, what is the infinite sum of this series of 18 times 0.98 to the k minus 1, right? So as that goes to infinity, because r is, the absolute value of r is less than 1, right? We know this is a convergent geometric series. So this sum is going to converge to some number as the number of swings goes out to infinity. And so essentially, at infinite time, it will eventually stop, which means in some sense, I guess it will never stop. But assuming we could get out to infinity in time, what will the total distance it have swung become? And the reality is, once you get to a certain point, the swings are going to be so small that they're really adding little to the distance anyway. So effectively, how far has it swung? And because we know that this is a converging series, we can use the formula a sub 1, which is 18 over 1 minus r. And that'll get 900 inches. So the total distance traveled, the total distance swung is going to converge to 900 inches as the number of swings goes off to infinity, right? Because it's slowing down over time. All right, so that's pretty much all you need to know about converging and diverging geometric series, and that's the last topic of the summer. So we have officially completed pre-cal for the summer here. You've covered all the topics that you're going to see on the final. I'm going to take a picture of the homework in a second here to give you for tonight, and then over the weekend I will finish up getting you the tests and the practice tests for the different units, as well as the solutions to those practice tests. The final, I said this yesterday, the final is going to be on August 21st. That's a Thursday at 10 a.m. in room 28. And I haven't heard from anyone that that's not going to work, so that is the day that we are going with. So, and there's your homework for tonight. So that's it. Do the homework, go over the practice tests, and be prepared for the final on August 21st at 10 a.m. in room 28. Other than that, have a great summer. Great rest of the summer, I should say.